What we're going to do is we're going to look at this problem where we can compare the approximate values with the actual values. We are going to consider the initial value problem. Y prime is equal to 0.2 times xy, and the initial condition is y of 1 equals 1. So x naught is 1, y naught is 1. We're going to use Euler's method to obtain an approximation of y is equal to 1.5, and we're going to first use 0.1 as our step size, and then we're going to repeat the whole process and use 0.05 as our step size. And what we want to do is at each one of our steps, I want us to calculate the following values. That is, I want to look at n, I want to look at x sub n and y sub n. Now that's the part that we created last time in Excel. And now this time I want us to include three new columns: the actual value, the absolute error, and the relative, or the percent relative error. Now what are those three new columns? Of course, actual value means if we knew what y was from the beginning, we could compare our approximate solution from Euler's method to our actual solution that we know. Of course, in general, we won't know that. I mean, that's the whole purpose of numerical analysis, of doing these quantitative approximations, is when we don't know the solution. But to see how well our method works, we'll consider cases where we know the solution and see how it performs. Okay? So that's what I'm doing here. Now, the two errors that I have on the screen are actual, or two in the columns, actual error and percentage error. Actual error, or absolute error, sorry, is the absolute value of the actual value versus the approximation. So this column right here is going to be, I'm going to subtract, and I'll put this in blue, this column and this column here. I'm going to erase that in just a second. But I'm going to subtract those two and take the absolute value. So that the absolute value means I always have a positive measure. I don't really care which one's bigger, which one's smaller. I just care how far apart they are. And then for relative error, I'm going to use this formula that's down here. Okay, you take the absolute error, and there's a typo, that should be a T in there, absolute error, divided by the absolute value of the actual value times 100. So this is how far are you off percentage-wise from the actual value. How far away is your approximate value from the actual value as a percentage of the actual value? Okay? This would allow us to compare methods where, say I'm approximating a problem where the scale of numbers is in the thousands, right? So my output of my functions is in thousands of dollars or something like that. And then another problem I'm working is in like 10 to the minus 6 range. So it's like 0.0000367. If I compare just absolute values, then I'm only getting the scale that represents the actual size of the numbers of the problem I'm working in. If I want to be able to compare across different examples, different model problems, how the Euler's method is doing, I would want to look at the percentage relative error. So that's the column I'm going to add in there. But the beauty is these are all formulas that depend on specific values in the row, which make Excel an ideal tool for this kind of approximation. So I'm going to switch over to Excel, and I'm going to put those 6 columns in there using the function that we have up here. So let me go ahead and write it down so we have it handy on the board. It is y prime is equal to 2xy. So there's my f. Y of 1 equals 1. There's my x naught. Sorry. There's my x naught, and there's my y naught.
And y prime is 0.2.
See point? Oh, thank you. Sorry. That would make a big difference. Thank you. Our goal is y at 1.5, and we're going to use h is equal to 0.1, and then we're going to repeat it and do h is equal to 0.5. We're doing this problem twice. Okay. So let me close this. And we are now back here. So my columns are going to be in x sub n, y sub n, and actual value, absolute error, and percent relative error. Now, I did give you the solution, didn't I, at the bottom of that page in your notes? Yeah, so we can refer to that. Grab this and bring this over here. All right, so n equals, of course, let's do this too. I'm going to come off to the side over here in G, and I'm going to put H equals, in fact, I'm going to make that right justified, and then in the H1 cell, I'm going to put my first H that I'm going to use. So I can refer to that cell in my formulas. So for n equals 0, I know that my x sub 0, my first value of x is 1, and my first value of y is also 1. Okay, now for my first value of n equals 1, I'm going to take my previous x value using my formula for Euler's method. It's the previous value of x plus whatever my h is. So using Excel, I'm going to use formulas equals the cell above it, which would be B2, or I use my up arrow after I hit my equal sign, plus my h value, which is H1. But remember, I want always to refer to H1. I don't want to refer to a cell that's 7 over and 1 up. I want to always refer to H1. So I'm going to put $H, $1 for absolute referencing. Remember that from last time? So all this formula is it's using the Excel formula system to do previous value of x plus h. I hit that, I get 1.1, which is exactly what we would expect. And of course, y sub n is going to be the previous value of y, so equals C2 plus the value of h with the dollar signs in there times now my formula. Now my formula in this case comes from here. That is, it comes from 0.2 xy. So I need to plug in here, and I'm going to put it in parentheses just so that I know that this is my function. Parentheses 0.2 times x times y. Now, which x and y am I plugging in? The previous one. So it's 0.2 times x times y. So everywhere there's an x, I'm going to put B2. And everywhere there's a y, I'm going to put C2. So that means times B2 times C2. There's 0.2 xy. And there's an approximate value. So before I add these new columns, let's just go ahead and do what we did before. If you select and highlight that entire row, those 3 cells we just made, because they're all designed now with our absolute and relative cell referencing, if I drag this down, it's going to fill that up just the way that I want it to. In fact, I'm going to go all the way down to row 7, that is n equals 5, and I will have my approximate value. 1.12588 is the approximate value of my function at that point. In other words, hello? Oh, my pen went off again. Dadgummit, it's got a timeout feature on it, I guess. Hello? Wakey wakey? So this number right here, actually do this in red, this number right here says that y at 1.5, the actual function, is approximately, not exactly, but approximately equal to 1.12588. Okay? Now what is y at 1.5 actually equal to? Well, because we have the formula, we could solve this differential equation. It's separable, it's actually linear, so either of those 2 techniques would give us an answer. We could find the solution. Let's use the solution that's given to us right here. Namely, let me exit my annotation mode. Come back over here. Let's find the actual value of this at each value of x. Okay? Since this right here, in fact, I may even emphasize this by putting the fact that this is y. This is the actual y value. I'm going to use the formula for the solution. Now, it only depends on which x I'm at. So, this is going to be equal to the exponential, so exp of 0.1 times the value of x, which is for that row, right? This right up here is the value of x I want to plug in. I want to find the y actually at this point. This column is the y that's approximately there. This y is the one that's exactly there. So I'm going to put in there and put that into my formula for x. So that squared minus 1, close the parentheses. Oh, I need a times in here. And I need to close the parentheses. Okay, and hit enter. And of course, I better get 1, otherwise I had the wrong function in there because I've already told you that y at 1 is equal to 1. Okay, now before I move on, any formulas you need to go back and let you see again? Did you miss anything? Where are you off? There's my formula. EXP is the way that you, in Excel or just about any other formula-based system, like on a computer, if you're going to enter exponential, e to a power, you're going to use EXP as the function. Okay? Now if I drag this little handlebar down, those are all my actual values of this function, right? This number right here, say this guy right here, that is y at 1.1. Whereas this number right here is y at 1.1 approximated. Right? Euler's method guesses that using its little strategy for following a line, that the value at 1.1 for my solution should be 1.02. What's the actual value at that point? 1.021222052. That's the actual value. Okay? So how far off am I? That's where we calculate the error now. So the absolute error will always be the absolute value of the difference between the actual value and the function value. So equals ABS of the actual value minus the approximate value. That's the formula that you have in your notes. Absolute value, the actual value minus the approximation. And of course, the error at your starting point is 0. Why? The starting point. You already know it. It's not approximated, it's exact. But every point after that, guess what? It increases. So that gives you the absolute error, and you'll notice it's increasing. The further away you get from your original point, the worse your error actually is. And then how do you calculate percent relative error? What would be the formula there? In absolute value. So you're going to take the absolute error, which in our case is for that row, the absolute error at that point would be E2, divided by the absolute value of the actual value. And you're using the actual value because you want to know how far you are off from its true value as a percentage. And I'm also going to multiply times 100, so it's in percent form. Now in Excel you can either do that or you can just switch the cell mode to be percents. Either way works. I'm going to go ahead and just put it in as times 100. And this gives me my percent relative error. And the reason why we do absolute value here too is because we don't want signs involved. We always want a positive measure of error, an absolute distance. Because whether we're above or below doesn't matter. It's how close we are that really matters. Of course, that's 0 all the way down. Now that's 0.64% error at our last iteration, at our last value. Okay, so I tell you what I want to do. I want to actually take this and copy it because I want to compare 0.1 to 0.05. If we take smaller steps, the question is, what happens here? Do we improve our error? How much do we improve our error? If we cut our step size in half, what happens to our error? Okay? So to do this, now, has everybody gotten to this point, or do you have any questions about how to do this? Like I said, I've recorded this as a quick little video, so I can post this on Blackboard, and you can also review this again as you're working on your homework. Okay, any questions before I do the next one? Okay,
yeah,
so
you just click on the cell for the relative error, so I see the formula.
yeah, it was the absolute error, which is E2, divided by the absolute value of D2. Times 100. Okay.
And I think I might be off on Y sub n.
So its formula was, like for what, when you're in the second row, it was C2 times the $H $1, so it's always referring to that cell, times 0.2 times B2 times C2. Okay, and then I dragged that down. In fact, by the way, because all these formulas are relatively based, I could go further, but I really don't. I mean, if I drag this down, notice I can get 1.6. But the question of the particular problem we're working on only asks for going through 1.5, so that's why I stopped there. Took me 5 steps to get there. Now, if I cut the step size in half, it's going to take me twice as many steps to get there, but the question is, how does my error respond to cutting my step size in half? So let's just copy this sheet. Okay, I'm going to right-click down here where it says Sheet 1, and I'm going to say Move or Copy, and I want to create a copy of this cell. I want to move it to the end, so I'm going to have just the exact same spreadsheet again, and then I can go in and change my 0.5, and that way I can refer back and forth between the two sheets. So right-click on Sheet 1, Move or Copy, move to end, and create a copy. Say Sheet 1 again. Now let's change this value over here. Notice these two sheets are exactly the same. So I'm going to change the second one to 0.05. Okay, and problem is this is now not anything relative to 1.5. I want to know what the error is at 1.5. So I got to take twice as many steps. So I'm going to drag this all the way down until I get to 1.5, and there it is. Are you with me? Copied the cell. This one over here, spreadsheet 1, tells me what the absolute error and relative error, percent relative error, is at 1.5 if I used a step size of 0.1. Okay, now sheet 2, after I changed my H to 0.05 and I selected the cells from A7 to F7 and then I dragged my little bar down until I had a total of 10 rows all the way down to row 12. That is, n is equal to 10 here. I now have my x value of 1.5. So I can see that the method approximates the solution to be 1.12947. The actual value from the formula, which we know is the solution, is 1.133148453. So there is a difference of an absolute value, in absolute value of 0.0036816. And percentage-wise, it's now 0.32% off. Now, how far off were we in the 0.1 case? 0.64. What happened to the error when we cut the step size in half? We cut the error in half. Okay? As a matter of fact, that is the key property about Euler's method that makes it a bad choice. Okay? What you want is something much better than that. You want the error to respond much better to cutting your step size in half than just cutting itself in half. Okay? That method right here says this is what's called an order H method. It behaves exactly like H does. Cut H in half, cut your error in half. Cut H in a fourth, you'll cut your error in a fourth. Okay? Now, what you really want to happen is something like H squared or H cubed or H to the fourth. If you can find methods that behave like those, you've got a whole much better choice. One of our favorite methods is called the RK4 method, which is an order H to the fourth method. If you cut error in half, what is 1/2 to the fourth? If you cut H in half, If something is order h to the 4th, that means your error is basically going to be cut in 1/16. Taking a half smaller step, you get 1/16 of the error you originally started with, which is a whole lot better than just behaving exactly the same as h does. So that's why Euler's method is not a good choice, but it's still easy to implement. A little bit harder to implement RK4, which is one of the gold standards and commonly used techniques for that. All right, so do you know enough to build these spreadsheets on your own now? Or at least can refer back to this video, I hope. Any questions before I close this out and move on to section 3.1? All right, I'm going to stop that recording.